Hey everybody. Today we're talking about moment generating functions with a focus on the discrete case. We're in a situation where we have a random variable x and we want to find the moments of that distribution. In particular, the expected value of x, the expected value of x squared, x to the third, etc. The moment generating function is going to help us do that. The definition is slightly technical. The moment generating function, m of t, is a function of a kind of unrelated variable t that just has sort of a technical purpose. And it's defined to be the expected value of e to the tx, as long as that expectation is defined in some neighborhood of t equals 0. If x is discrete, which again is the focus in this video, that expected value can be written out as a sum, because the way we do expected value of some function of a random variable is we take the values that that function of the random variable can take over the support of the random variable, and we weight each one by the respective probabilities of the corresponding values of x. Throughout this video, small f is going to be the probability mass function of the random variable, and s is going to be the sample space. Here's a simple example. We have a distribution of a random variable x. X can take exactly 4 values, 3, 4, 8, and 10, with probabilities 0.3, 0.3, 0.2, and 0.2. Just plugging into that definition, we take each of the values of x, we do e to the t times x, and then multiply by the respective probability. So we get like 0.3 e to the 3t plus 0.3 e to the 4t, etc. Notice the form of this moment generating function, this MGF. The exponents contain the possible values of the random variable, and the corresponding coefficients are those probabilities. So here you can see the values of the random variable in those exponents, 3, 4, 8, and 10, and the probabilities 0.3, 0.3, 0.2, and 0.2 corresponding to those. And this pattern is going to hold true for any discrete random variable that has finite support. The moment generating function can be used to find the raw moments of x. Again, expected value of x squared, etc. And this is the real value of the moment generating function. To say it in words, the kth derivative of the moment generating function evaluated at 0 is the kth zero-centered moment. The proof is really direct, so I'll just flash it at you without dwelling on it in depth. We're using the definition of the moment generating function. That's the summation you're seeing just on the first right side of that equality in the top line. And then the kth derivative here can get moved inside the summation. And when we take the kth derivative of e to the tx, with respect to t that is, we get a power x to the k times e to the tx. And so then when we evaluate all that at 0, we get x to the k times f of x summed up over all the x's in the support of the random variable, which is just the expected value of x to the k. Here's an example, an immediate application of the moment generating function, finding the mean and variance of the geometric distribution. So we'll do that again by finding the moment generating function of this random variable. This is a good place to pause the video, try it on your own before advancing. So we're just applying the definition, the moment generating function, e to the tx times f of x, summed up over the entire support, so from x equals 1 to x equals infinity. Plugging in the probability mass function, f of x, is q to the x minus 1 times p, where p is the probability of success on any given trial, q is the probability of failure. So remember, the geometric distribution is modeling the number of attempts needed in a sequence of Bernoulli trials before you get the first success, or rather until you get the first success. We can expand out that summation into an infinite series, p e to the t plus pq e to the 2t, etc., and then consolidate that down into a summation. And I've done that in a slightly creative way so that I can write the thing in the inside the summation as all having a power of x. So q e to the t all to the power x. And the reason I've done that is because now I can see I have a geometric series with ratio r equals q e to the t and initial term a equals p e to the t. And of course we know geometric series converge when the ratio is less than 1, and we have a formula for what they converge to. The formula for what it converges to is a over 1 minus r, again assuming the absolute value of r is less than 1. So overall, as long as t is less than negative ln of q, we get the moment generating function of a random variable with a geometric distribution is p e to the t over 1 minus q e to the t. So we can find the expected value and variance by just differentiating this twice, plugging in t equals 0 into the first derivative and the second derivative, doing our usual stuff to find expected value and variance. So here's the calculation for m prime of t. It's done using the quotient rule, and I won't dwell on it here. When I plug in 0, I get 1 over p. And that's kind of intuitive, like if I'm doing a sequence of Bernoulli trials, like rolling a die or something, say with a probability of success of 1 in 6, the number of trials I'm expected to need before I get the first success, like maybe the first 2 that I roll, is 1 over p. So in that example, it would be expecting 6 rolls. Similarly, we can get expected value of x squared by taking the second derivative of the moment generating function, plugging in 0, and we get 1 plus q over p squared. Now, that's not exactly the variance yet. The variance is given by the formula, the expected value of x squared minus the expected value of x quantity squared. So we plug in the two things that we found, the expected value of x squared and the expected value of x. We do a little simplifying, and we get a variance of q over p squared. So that means that the standard deviation of a random variable with a geometric distribution is the square root over p. This fact is often useful. The moment generating function completely determines a random variable. So if you have two random variables, x and y, with the same moment generating function, then they have the same distribution. So for instance, I can give you a moment generating function, like this one, and ask you to determine the probability mass function in support and have it be an actually meaningful question. Again, before we wrap up this video, pause the vid, give this a try on your own. So in this case, the random variable x can take 5 different values. Remember, that goes in the exponent of e to the tx. So the corresponding probabilities then are 0.1, 0.2, 0.2, 0.4, and 0.1. The support of this random variable is going to be those exponents 0, 2, 4, 6, and 8. The 0.1 at the beginning of that moment generating function, by the way, is corresponding to 0.1 times e to the 0 times t.